So what is particle physics? Well, if you think about your GCSE chemistry lessons and you think about the product table, you've basically got loads and loads of different elements, the lightest of which is the hydrogen element. And inside each of these atoms of these elements, we have the nucleus, which is made up of protons and neutrons, which you discovered at GCSE. Physicists over time actually, with the aid of this experiment here called the Large Hadron Collider, which is the largest physics experiment in the world. It's got a 27-kilometer circumference underground tunnel underneath Switzerland, and it basically smashes these protons together. And if we can see in these images here, we get various collisions producing these smaller particles, which physicists have categorized in what they call the standard model, as shown here. Now, there are two types of fundamental particles, as shown in this table here. So when we talk about hadrons being matter, matter can be split into two categories, one being baryons and mesons, okay? But on top of that hadrons, there is another category called the leptons, okay? So if I go back to this table here, these guys make up the hadrons. So the purple particles here, they're not purple in real life, but obviously to make it clear, to separate these various particles, let's call these purple particles here the quarks, and they make up these guys, the hadrons, which can be broken down into two further categories. There are also these green particles, again, not green in real life, but they make up leptons, okay, which we'll go through later on in the lesson. These red guys here are also particles, but they are particles in the sense that they are responsible for the four fundamental forces, okay? The gluon is responsible for the strong force, which we'll talk about later on. The photon is responsible for the electromagnetic force, and the Z and the W bosons are responsible for the weak force, and the graviton, which is not technically discovered just yet, is meant to be responsible for the gravitational force. Okay, hence why the graviton is not on this chart here. And the Higgs boson was the most recently discovered particle or boson, and it's said to give these bosons their mass because these guys don't have mass, especially the photon. So let's move on. So speaking of the quarks, there are three different flavors or variations of them. So we start off with the up and the down quark, and actually the up and the down quark make up our proton. So if we look at this here, a proton is made up of two up quarks and one down quark. We'll talk about their charges in a second. And the neutron is made up of two down quarks and an up quark. Okay. Then charm and strange are a little bit heavier and they're more unstable, and we'll talk about instability later on in the lesson. And then we have top and bottom being the heaviest and again being more unstable, and they tend to decay. Likewise, as I said, we've got leptons and their respective particles increasing in mass. So if you think back to your GCSE chemistry or physics lessons, the electron is the only particle that actually remains unchanged. So protons, just remember, are made up of these guys, the up and the down quarks, and the electrons. We'll come back to these bosons in a second, but just want to note that the gluon and the photon have zero mass, whilst the Z, naught, and the W plus and minus bosons for the weak force are heavier and contain mass. And let's look at their charges. Well, the gluon, the photon, and the Z naught boson have a zero charge, whereas the W plus and the W minus boson have got charges. Okay, so again, pause the video at any point to make notes so that you're confident with these properties that these particles have. So let's look at hadrons. So hadrons have got two types of categories. We've got the baryons, which are made up of three quarks, okay? And I said the most common ones we know are what you've already encountered at GCSE. So the protons made up of two ups and one down quark, as shown here, and the neutrons made up of two down quarks and one up quark. Then we also have got the meson category, which is made up of two types of quarks, only two. But the important thing here to remember is that there is only going to be one normal quark and one anti-quark. So I've used that word for the first time, anti-quark. It is an example of what we call antimatter. So antimatter is basically standard matter, same mass, same shape, but the only difference it's got the opposite charge if it does indeed have a charge. Okay, so that's what that represents, and there are two types of mesons you need to know for the AQA spec, which is the pions and the different charged pions, and the kaons, which are heavier mesons. And of course you would have your antimatter equivalents. So your antibaryons would be the respective symbols, but you would basically put like a bar or a horizontal bar on top of the letters to represent them being antiquarks. Likewise, if we look at a standard meson here, so we have a standard quark and an antiquark, the anti-equivalent of it would be that quark becomes an anti and the anti becomes a normal quark. Likewise here, so let's look at the proton or the antiproton equivalent. So antiproton equivalent is an anti-up, an anti-up, and an anti-down. Anti-neutron is an anti-down, anti-down, and an anti-up. Just want to talk about the charges really quickly. So let's look at this table here. So an up and a down charge have got charges plus 2/3 and minus 1/3 respectively. Okay, so if we do the maths, plus 2/3 plus 2/3 plus a minus 1/3 should give you plus 3 on the top and 3 on the bottom, so that becomes a plus 1. Okay, so make sure you're confident doing that. So write out plus 1/3 plus 1/3 plus 2/3, plus 2/3 plus minus 1/3. It should give you 4 take away 1, which is 3/3. Okay, on the top for the numerator, and the denominator stays the same. Let's look at the neutron. So it's plus 2/3 for the up quark, minus 1/3 plus another minus 1/3 gives you a 0, 2, minus 1 on the top over 3. 0 divided by anything is 0, hence why the charge is going to be 0 for the neutron. Okay. We'll come back to, all right, let's talk about the 4 fundamental forces now. So as I said, the strong force is going to be a new type of force, or a new name for those doing A-level physics for the first time, especially if you've only done GCSE, and it is said to hold these quarks together. If you think about it, we have got a plus charge here, a plus charge here, and the law of electrostatics states that plus charges or minus charges tend to repel one another, and in this particular case, we therefore have to infer that there must be some sort of force keeping these up quarks and down quarks together. And that's what scientists have postulated as the strong force. Now, in terms of the strength of the strong force and range, this table here is very useful, because actually the strong force, when you go super close, so theoretically if we had an up quark and a down quark interlocking, going really close to one another, less than 1 femtometer, for example, that strong force would be repulsive. Okay, so the strong force actually keeps the up and the down quarks at bay, but also glued together, so to speak. Okay, because we know, according to this table, that there is also going to be a repulsive force between positively charged particles. okay? But um, the strong force keeps the quarks together, okay? And this graph, sorry, shows us the range of the um, strong force. So we can see about 1 femtometer, we have it being very, very attractive, attracting these nucleons, sorry, the quarks together. And then it's got such a small range that after about 1.5 femtometers, we really don't see it. So basically, we as humans, we don't experience it. Anything on the macroscopic level, we don't experience it. Hence why you probably have never heard of the strong force before. Okay. So again, pause the video at any point. This graph, either one of these are useful to actually remember, or at least have an idea of how the strong force and the electrostatic force behaves. Okay. So this table here shows us the range. So we can see the strong force has got a very, very small range as shown in that graph earlier on. The electromagnetic force does have an infinite range, however, it does fall off um, the further you are from the charges. The weak force also has got a small range, and we'll talk about the weak force in a second. And of course, the gravitational force has got an infinite range, but again, it falls off uh, the further the distance is, or the greater the distance is. Okay. So again, in terms of the types of particles, we talked about the bosons. So for the strong force, it would have been the gluon. For the electromagnetic force, it would have been the photon. And for the weak force, you have three types of bosons. And for gravity, we have a hypothetical graviton. Okay. So again, just a couple of notes there. Pause the video at any point if you want to make sure you get these notes. I'm basically just going to be summarizing the key points. Right, let's now go back to what I was saying earlier on. I talked about antimatter forces. Okay, I want to now talk about quantum numbers. So if we look at this table here, so again we have the respective quarks listed, up, down, strange, top and bottom, or charmer not there, but they follow the same pattern in terms of, if you remembered, up, down, top, bottom, charm, strange, it's always going to be plus 2/3 as the first one, minus 1/3 for the second one for the charge. Now, with regards to strangeness, the only quark that will have a value of strangeness, which will be -1, will be the strange quark. Okay. Now, the common question among A-level physicists is, what is strangeness? And again, as the name suggests, it is a very strange quark. Okay. No pun intended. But for all intensive purposes, physicists have attributed this quote unquote quantum number or label onto this strange quark to help with mathematical calculations in particle-particle interactions, which we will look at them later on in the lesson. But all you need to know for the exam is that these strange quarks have got a strangeness of -1, and an anti-strange quark has got a strangeness of +1. Okay, so again, pause the video at any point to make sure you're confident and you can recall this from memory. I want to talk about the baryon number. So the baryon number, again, is another example of a quantum number, or just a label that we put onto these particles. And each one of these quarks, if they're normal quarks, have got baryon number of 1/3. So 1/3 for each of these guys. And if they're the anti-quark equivalents, they're going to be -1/3. Okay. Also, pay careful attention to the charges. For the standard quarks and the anti-quarks, they're basically opposites of one another. Yeah. Likewise with the strangeness. Is there anything here I need to highlight? This is just showing us the relative masses, how the electron positron mass is a lot smaller than the neutron and the proton, and also you can see their relative masses, or their actual masses actually, and these are given in your data sheet, which you'll have in your exam. And the neutrino and the antineutrino, which are examples of leptons, which I haven't um, gone into too much detail just yet, but just know for now that it is a lepton, and they've got pretty much no mass, okay, or very, very little. Okay, this is a useful table. Again, pause the video, make sure you are confident with this table. Um, some of this information will be given in your data sheet, especially with the rest masses. Again, you don't need to know the rest masses off by heart, you just need to know the trend, relative trend. But this is a nice table that shows you the different particles and the type of forces that they interact with and their charges, and rest energy, symbols, and so on. Okay, so pause your video to make sure you're confident with that. Now I want to now go into these guys here, the pions and the kaons. Remember when we talked about hadrons, there were two categories, one being the baryons, which were the 3 quarks, and the other category were the mesons, where you had 1 quark and 1 antiquark. So let's look at the 6 types of mesons you need to know. And there are two categories. One is the pion, or the pions, which are the lighter of the two, and then the kaons, which are the more heavier. And I want to show you this table in particular, which is one I would recommend memorizing literally from the start of your A-level physics course. Maybe put it as a poster, do it on an A4 sheet of paper, put it in your room or somewhere, maybe have it as a screensaver, or background screen of your phone or computer. Over the course of the year, you're going to remember it. What is this showing us? Well, this is showing us the constituent quarks of the pions. So the pions are the mid section here. So the pi neutral, the neutral pion, sorry, is made up of a anti-U or a U, a D, and an anti-down. I'm using U and D up and down interchangeably. And likewise, you see the respective constituents of the kaons above here, up there, and down here. Okay, so make sure you are putting this to memory. Again, pause the video to make sure you get this down. So those are mesons. Okay, mesons tend to decay into lighter mesons, such as pions, or smaller particles, such as other leptons. And I want you to think about your GCSE lessons when you were doing radioactive decay and you learnt about uranium, for example, and heavy nuclei, which were unstable. They basically emitted alpha, beta, gamma radiation to become more stable. It's the same thing with these particles. The kaons are heavier, are more unstable, and they are going to decay into the lighter mesons and lighter leptons, more stable fundamental particles. Okay. Want to talk about the pion as well. So the pion actually is a bonding force between the neutron and the proton in the nucleus. This is a Feynman diagram, which we'll look at in a second in more detail. But the pions, which again is an example of a meson, is responsible for acting out this force between the neutrons and the protons in the nucleus. Okay. So they act out the strong nuclear force. Okay, and this is a nice diagram here where, and again, just to clarify things, the gluon is the gauge boson for the strong force. However, we have the baryon meson being present inside the nucleus as well, producing that bond. And if you look at this Feynman diagram here, again, just for clarity, you do not need to memorize this. I'm just showing you this, that the gluons represented by these swirly lines here are actually keeping the ups and the downs together, but also they are responsible for producing this pion here, which is, as you can see, interlinks this neutron with this proton and that neutron with that proton. So it is very complicated, um, or it looks like there's a lot of information there, but put simply, all you need to know for the exam is that the pion is the exchange particle for the strong nuclear force between the protons and the neutrons. And there are three versions of them, and kaons are heavier and they decay into these pions and lighter fundamental particles such as leptons that I mentioned earlier on. Okay. So here is an example of a kaon decay. So a neutral kaon can decay into a positive pion and a negative pion. Okay. Some useful information here. Again, pause the video at any point. I'm just highlighting the key bits. Again, this is just a summary of some of the information I've already mentioned. But again, pause the video so you can make notes. Okay, I'm going to move on. So I talked about baryon number. Let's think about a baryon. So again, a baryon, remember, is made up of 3 quarks. So if each of the quarks had a baryon number of 1/3, as shown in the table here, 1/3, 1/3, 1/3, it gives you a total baryon number of 1. Yeah, 3/3 gives you 1. If they are anti-baryons or anti-versions, then they're obviously going to be these guys here, -1/3 plus -1/3 plus -1/3 gives you -3/3, which simplifies to -1. So an antiproton or an antineutron will have baryon numbers of -1. Likewise with the mesons and the leptons, because we have one antiquark and a normal quark, for example, we could have a down and an anti-strange. Yeah, that would be -1/3 and +1/3. It would give you a baryon number of 0. In fact, a good exercise is to go back to this table here and using the baryon numbers, just ensure that all the baryon numbers are 0. So 1/3, -1/3, 1/3, -1/3, and so on. Okay. So the baryon number, and we're going to talk about Feynman diagrams now, always has got to be conserved in any particle interaction. Okay. And we'll do some examples later on, showing you these Feynman diagrams. Now, for the AQA specification, you just need to know about the second heaviest lepton, which is the muon. So you don't need to worry about the tau, just be aware of it. So this third one here, the tau and the tau neutrino, at AQA, as I said, these guys are the only ones you need to technically remember up to, but it won't hurt you to know that there is one larger lepton or generation of lepton. Okay, so let's focus on these guys. So muons are normally found in cosmic rays. Obviously, these are radioactive particles or particles just traveling through space, and we tend to see them at the northern lights near the North and the South Pole, where the magnetic field and electric fields are stronger. So that's what we see at the northern lights when these particles interact with those fields and enter our atmosphere. So these are the symbols. So the muon is this Greek letter here, this weirdly huge shaped letter, and it's got the same charge of the electron, but it is heavier than the electron. Okay, and like what I said earlier on with GCSE, heavier nuclei being unstable and they would decay, the muon, because it's heavier, would decay over time into something more stable, such as the electron. Okay. Again, this is a useful table, and let me talk about lepton number actually now. So this column here is the electron lepton numbers. This column here is the muon lepton numbers. Now, although I've distinguished electron, muon, lepton number, actually you can categorize them all as being lepton numbers. Okay, so the standard leptons, which is the electron and the muon, have got lepton numbers of 1, and an anti-electron and an anti-muon would have lepton numbers of -1. It's not shown on this table here, but just be aware of that. The electron neutrino is an example of a standard matter, as is the muon neutrino. Their masses are a lot smaller, but yet they will have lepton numbers of +1, and then their antimatter equivalents, if we put a bar on top of them, would be, they would have, these guys here, you would have a lepton number of -1, respectively. Yeah? And you can see the masses here. So the electron neutrino has got a very small but not non-zero mass. Muon heavier than the electron, and the tau a lot heavier as well. Okay, so you can pause the video at any point. Just want to highlight as well that the antimatter equivalent of the electron is the positive positron, which is shown here, and we write it with an E and a plus. Okay, the muon minus, and then the anti-equivalent of it, we put the plus sign there. Now, neutrinos were discovered when scientists or physicists found that in certain collisions that some energy was missing, and this later was found out to be these other smaller particles which would account for this missing energy, and we call these guys the neutrinos, and they're really useful when we talk about the Feynman diagrams or particle-particle interactions with the conservation laws. Okay, but actually there are loads and loads of neutrinos passing through your body every second from the cosmic rays from space. Okay, so they're literally got zero mass and they don't affect us as far as we know. So I talked about lepton numbers, +1 for standard leptons, -1 for anti-leptons, and then importantly, the lepton number for both types of hadrons, the baryons or mesons, are going to be 0 because they're not classified as a lepton. Alternatively, these guys here, the leptons and the anti-leptons, will have a baryon number of 0. Okay, so make sure you remember that. So baryon numbers only refer to hadrons, and lepton numbers only refer to leptons, both anti-leptons and normal leptons. Okay. Again, just some more information there for you to jot down at any point. Pause the video. Talked about strangeness. Again, pause the video if you want to get any of that down. Right, I want to talk about strangeness in terms of conservation. So remember, we talked about strangeness only being present in the strange quark. If you look at the kaons, we notice that they're made up of the strange quarks. Also, one of their constituents are the strange quarks. Okay, so S, 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 and the pions have got no strange quark in them. This is because the kaons are a lot heavier, and are unstable, and they will decay into these pions. So in terms of strangeness, when a kaon decays via the weak force, the strangeness is not conserved. Okay, we can see that here. However, if we are going to form some kaons via the strong force, and gluons can come together to produce kaons, put these quarks together, we basically have strangeness being conserved. What do I mean by that? Well, basically we get kaons coming or being produced in pairs. So if I show you here, for example, so when kaons are produced, they always come in pairs, for example, of K plus or K minus, okay? Or they will produce two K naughts, for example. But basically, the strangeness will always cancel out. So minus one and a plus one particle of strangeness will cancel out, okay? So an anti-strange and a strange will cancel out. So if we go back to the hexagon here, so this K plus and this K minus would have been produced. This with a standard S and an anti-S would also be a combination, okay? So that is how you can tell, or it's worth remembering is that strangeness is conserved with the strong force when these kaons are produced, not decayed, but the strangeness is not conserved when the kaons go from one of these guys into two of these guys, for example. Yeah? Because we have strangeness at the beginning, but we have no strangeness at the end. And that is what examiners like to check your understanding for. And look at this is the example K naught here with a strange quark, and it decays into these guys with no strange quarks. Yeah, so there you go. Uh, please pause this video to make sure you make a note of these points here so that you are confident in your exams. Let's talk about muon decay. As I said, muons are heavier than the electrons, and they can decay into the lighter electron and electron neutrinos, and a muon neutrino in this case. Which brings me into, and we're coming near the end, into Feynman diagrams. Feynman diagrams are what these guys are here, okay? Now, they are named after a famous physicist called Richard Feynman, and he basically created them to show us particle interactions with these force carriers. So what do we have here? Well, we have a negative muon, and via the weak force with a W minus boson, we get a decay producing a muon neutrino and an anti-electron neutrino plus an electron. Now, remember what I said about conservation laws? Let's look at the charges. Let's see if charge is conserved. So we have a minus charge at the beginning. This is a neutral charge, and a minus charge in the end. So charge is conserved. Let's look at the lepton number. Well, this has got a lepton number of +1. It's a standard lepton. This is a standard lepton. It's a muon neutrino. So we got +1 here. This is an anti-electron neutrino. So it will have a -1 of lepton number. So these guys cancel out. And then this is a normal electron. So this has got a lepton number of 1. So lepton number of 1 at the beginning. 1 minus 1, 0. And then 1 here, so that is conserved. Baryon number, 0 at the beginning, because this is a lepton, not a baryon. No baryons here. Baryon number is 0 at the end, so that is conserved. And you need to make sure you go over these 3 quantum numbers to check for their conservation. Now, students have asked about how do we know whether it's a W minus or a W plus boson. Well, there isn't actually a good general rule to follow because the general rule of thumb is normally the charge is being transferred. So you can see here that this W minus charge is being transferred from this U minus to the E minus here, okay? So it would make sense that this would be a W minus, okay? But there are different loads and loads of different Feynman diagrams, and my recommendation is, again, make a note of these so you can remember them. Let's look at these two here. So this is a neutrino interacting with a neutron. So this is an electron neutrino. So you can put an E there, an electron neutrino with the aid of a W plus boson is going to interact to produce a positive proton. Remember what I said about transfer of charge. Here we have basically got zero charge, but we need to generate a positive charge, and the plus and the minus obviously cancel out at the end, which ensures that the charge is conserved, because charge in the start is 0, plus 1 here, minus 1, they cancel out. Let's look at baryon number. Well, this has a baryon number of 1, baryon number of 1, baryon number of 0, 0, so baryon number is conserved. Lepton number of 1, lepton number of 1, lepton number of 0, 0, so we have 1, 1 conserved. Okay? Let's look at this Feynman diagram here. Well, we have two electrons interacting via the electromagnetic force. So this is showing us electromagnetic repulsion via the photon, the virtual photon, and we can see that the electrons repel, and it's acted out by this virtual photon here. We have lepton number of 1, 1, 2 at the beginning, 1, 1, 2 at the end, baryon number 0 at the beginning, baryon number 0 at the end, charge 2 minus at the beginning, 2 minus at the end, conserved. I think, have I done this neutron, neutrino? Yeah, this is the same thing. Okay, yeah, yes, I remember now. The reason I showed you this, remember what I said about the boson and not knowing what boson to put? In this particular case, we've put a W plus boson, so the plus charge being generated. But in this particular case, we're using a W minus. So it's kind of like radioactivity in terms of the randomness of certain particles being emitted, and in terms of the bosons, in this case, the weak force bosons, it's not always going to be W minus or W plus. And I've just shown you an example that in this case it's a W plus, but it can also be a W minus. Okay. Same thing for this one. So this is the same interaction shown here, but just with protons. So two protons coming together, showing you the electromagnetic force acted out by the photon. Let's look at the baryon numbers at the start. So we have baryon number of 1, baryon number of 1, baryon number of 1, 1, so 2, 2. Let's look at the charges. Plus 2 at the start, plus 2 at the end. And lepton number is 0 at the start because these are baryons, not leptons, and lepton number of 0 at the end as well. That's conserved. Right, I want to think back to GCSE now. Now, GCSE, remember we looked at beta minus or beta plus decay. If you did the Edexcel specification, you would have looked at beta plus decay. If you just did AQA, you would have only looked at beta minus. Nevertheless, we're now going to be looking at both of them, or looking at them into more detail. What do we see here? Well, the weak force is actually changing one of the down quarks to an up quark, and vice versa here. An up quark is becoming a down quark. Look at the signs. These ones I would say you have to remember. The examiners like to test your knowledge on these. What do we see here? Well, we have a W minus producing the negative electron that is going to be sent off. Okay, that's going to be emitted alongside an anti-electron neutrino here. And the down quark has got a charge of minus 1/3, and an up quark has got a charge of plus 2/3. Okay, so that is what is happening there. In terms of charge conservation, we would have to look at the bigger picture. So one of the down quarks in the neutron is undergoing this change, and one of the up quarks in the proton is undergoing this change to become a down quark, so that it becomes a neutron. So these are exactly the same diagrams, but this one is just like a zoomed in version at the quarks, and this is the macroscopic version of what's happening. The entire neutron, because of that change in quark, becomes a proton. The proton becomes a neutron. So let's now look at the conservation laws. So we have a barrier number of 1, barrier number of 1, barrier number of 0, 0. So barrier number is conserved. Let's look at charge. Well, we have a charge of 0, charge of +1, charge of -1. They cancel out. This is a neutrino, anti-neutrino, so it's 0. Charge is conserved. Let's look at lepton number. Lepton number is 0 at the start. Lepton number is 0 here. Lepton number of 1. Lepton number of -1, because it's an anti-lepton, so it cancels out. Likewise for this, barrier number of 1, 1, 0, 0, conserved. Charge +1, 0, +1, 0, charge is conserved. Lepton number of 0 at the start. Lepton number of 0. Lepton number of +1. No, -1, because it's an anti lepton, and a lepton number of +1, and they cancel out. Okay, so 0, 0. Perfect. Almost there, guys. And then this is an electron capture Feynman diagram. So the proton is using its electric field to capture the electron, and what's happening is that the positive charge from the proton is being acted out by the W plus boson, and that interacts with the negative charge of the electron to produce a neutron and an electron neutrino. So you can put an E there. Let's look again at the barrier number. Barrier number of 1, 0 at the start. So total of 1, 1 here, 0, that's conserved. Let's look at lepton numbers. Well, lepton number of 1, lepton number of 1, 0, 0, that's conserved. I think that's it. Yeah, charge +1, -1, 0, 0. So 0 at the start, 0 at the end. Almost there, I promise. E equals HF. This is an equation that's going to be given in your data sheet, and it relates energy with wavelength or frequency of light to Planck's constant, again, which is given in your data sheet. Why is that important? Because I want to lastly talk about pair production and annihilation. So let's start off with pair production. So if we have a photon of a specific wavelength using this equation here, so we can measure its frequency, we multiply that by Planck's constant, which is a constant of nature, we can get its energy in joules. Now, at any one point, that photon of energy can split into a particle and an antiparticle. Now, the sum of the respective particles, masses, and that mass has got to equal the original energy. So we're back to the old GCSE concept of the law of conservation of energy. We're not losing energy here. We're just changing one form of energy from the photon, which is the HF, into these rest energies, which we can relate to Einstein's famous equation E equals mc squared. And this is how scientists can work out the masses of these particles. Remember those tables I showed you earlier with the different rest mass energies? That's how the scientists can work out their masses, because we know c is the speed of light, constant of nature. We would divide that by the energy, and then we can get their masses. And we know there are two of them, so we divide by 2, and we can get their respective masses. Okay, so this is what we call pair production, and this is when we have a beam of energy, usually in the form of electromagnetic radiation, a photon, and splits into a particle and an antiparticle. And lastly, this is what we call annihilation. So this is when we have an antimatter particle and a standard bit of matter, and they collide and they produce two beams of photons of a set wavelength or frequency. So what we could do mathematically is represent 2e, 1e here and 1e here. So 1hf, 1hf, so it becomes 2hf. So we can write an expression of 2hf, represented by these two photons, has got to equal the rest mass total energy of this particle plus the rest mass total energy of this particle. Okay, so the rest mass times the speed of light squared of that particle, this rest mass times the speed of light squared of this particle, add them together, two lots of that, so 2mc squared has got to equal 2hf, the 2's cancel out, and that's your expression. And guys, that is the end of this lesson. Hopefully that was helpful. It was quite a long one. Again, do break down the video into chunks, especially when you're writing notes. But hopefully that's helpful. The next video, I will be doing some exam questions to help you apply some of this theory. But hopefully that's helpful. All the best in your exams.